Good evening mga lagan. So I've got another assignment here. We'll solve this really quick. So this topic is under strength of materials, stress and strain. So the problem is there is a shaft or like a tube. I don't know if it is clear. I will just zoom this out here. So we have two rod. We have the aluminum on the left, and then there is copper um, on the right. And then it is restrained at each end, like by a fixed support. Now the diameter of the aluminum is 50 millimeters, and then copper is 30 millimeters, and then the length of the aluminum is 300, then the length of the um, copper is 150, and then there is this force acting at um, the joint between the two material. So now let's zoom this out. So I drew the diagram again. So this is the aluminum. Uh, this one. So this is the aluminum, and then this is the copper, and then there is a force acting at the joint here, which is equal to 800 Newton or zero point 0.8 kilonewton. And then the length of the aluminum is 300, and then copper is 150. Then modulus of elasticity of the aluminum is 70 gigapascal, and then the modulus of elasticity for copper is 120 gigapascal. Now we have like if the material is subjected to a compressive force, it will contract. So if it is compression, then it will, let's write it below. So if it is, if the force, so we have two types of like forces that will be acting on this kind of like problem. So we have acted by a force, and then if there is also a change in um, temperature. So if the formula for the stress or the strain, if it is acted by a force, if it is in compression, or it is the same compression and tension, but for compression, the material will just contract, and then if it is in tension, the material will elongate. So the strain formula is, say, change in length. So it could be due to force or it could be due to temperature change. And then it could be a compression, like a contraction on your member, or a like elongation of the member. So this is equal to P, which is the force, then L, which is the initial length, and then the area times the modulus of elasticity. So if this is steel, then this is, or like in this example, this is aluminum. So this is L of the aluminum, and then area of the aluminum, and then modulus of elasticity of the aluminum. Now, if this is acted by like a change in temperature, so the changing length would be alpha then change in temperature times the initial length. Now, change in temperature, it could be from positive to negative temperature or a negative to positive temperature. So it doesn't matter if it is a if it is a positive temperature to negative temperature, it means the change in temperature is negative value. It means it will be really cold, then the material will contract. But if it is really hot, so this is in real life application. For example, if you have you might have noticed this in a bridge deck. So in a bridge deck, you have uh, you have this deck here, and then there will be another say if it's concrete deck. Now at the joints, if you notice, there is this some kind of like a finger joint, something like that one, and then also, oh no, not like that. It will be like, and then there will be like spacing. So this is like a like that one, and then there's another like a finger here, and then this will move depending on the temperature change. So if the temperature is really hot from the initial temperature, say for example at temperature would be say 25 degrees or 26 degrees, and then during summer when it's really hot, the temperature would go as high as say 40. So you have that change in temperature which is 14 degrees, and then if it is positive change, then it would expand. So that's why this one here is allowance. If you see this joint, this is allowance for contraction and elongation of your material. So you will see this like all bridges have this joint here that is for the change in temperature and also for like allow movement. But so whatever is the change in temperature and then the initial length and then your coefficient of the alpha is the coefficient of thermal expansion. But since in this problem, we are not given by in a change in temperature, only the force P, then we will be using this formula. The change in length is equal to PL over AE. Now, in the problem, so if we like this one, if we like the force is going to the right. Now, of course, our reaction would be going to the left. Um, so this is our aluminum, and then this is our copper, and then this is our force P here, this one at the joint. Now the reaction would be, since we only have one force P, which is acting to the right, all forces will be, or all reaction will be going to the left. So this is reaction at aluminum, and then this is reaction at copper. And then you have that equation, the summation of forces horizontal is equal to 0. So therefore, aluminum, reaction at aluminum plus reaction at copper is equal to the force, which is 800 Newton or zero point 0.8 kilonewton, or let's just say that is 800 Newton. So we have this first equation, this one. So this is our equation 1. Now, our second equation would be, now whatever is the elongation of the, um, so the force is right here at the joint. So when this force P is acting, it will pull the aluminum. But at the same time, it will push the copper. So to make it in equilibrium, you have the amount of like the change in length in copper would be the same as the aluminum. So the elongation of the aluminum will be the same as contraction of the copper. They should share the same length. So we can equate the two equations. So from change in length is equal to PL over AE. Therefore, we can say force at the P at aluminum times length of aluminum over area of aluminum, then modulus of elasticity of the aluminum material is equal to force P of the copper, length of copper, then area of copper material, and then modulus of elasticity of copper. Now, we have the length of aluminum, we have the diameter, we have the modulus of elasticity, then we have the length of copper, diameter of the copper, then we can solve for the area, and then modulus of elasticity of copper. So therefore, our unknown is the force acting on the aluminum and the force acting on the copper material. So therefore, like from equation 1, we have force acting on aluminum plus force acting on copper is equal to 800 Newton. That one. So therefore, we can say force aluminum. So P aluminum. So therefore, P aluminum is equal to 800 Newton minus P copper, right? Because the force acting on aluminum and copper is equal to 800. So if we have this formula, we will substitute to equation 2, which is PL. So this is PEL is 800 minus PCU over area of the aluminum is pi over 4 times 50 millimeter, right, squared. And then modulus of elasticity is, now this is in Newton, this is in millimeter. So we will have our E in megapascal. So aluminum is 70. So 70 gigapascal, or that is times 70,000 megapascal, which is Newton per millimeter squared. And then this is equal to ECU times, oh no, this is times L of aluminum is 300, and then P copper times 150, and then pi over 4 times this is 30 squared, and then times 120,000. So if we will simplify, so this one will cancel out. So this one 4 0, and then this is 4 0, right? And then what else? That one. So we will simplify this one here. So we have 800 times 300. So this is 800 times 300, then minus 300 P of copper, and then times 12, right? So this is times 12 times 30 squared, which is 900. And then the opposite would be 150 PCU times 50 squared times 7. right? So simplify. So this is 800 times 300 and then times 12 times 900 is equal to, so this is a really large number, 259 and then 200 and then 40. That one, 2592, then 6 zeros. And then this one is 300 times 12 times 900 is minus 324, then 40, then PCU is equal to this one, 150 times 50 squared times 7. So this is 262, then 5,000, 262, 262, then 5,000 PCU. Now we will combine the terms. So this is minus PCU, right? So this is minus 3,240,000 PCU. This one is 2,025,000 PCU. Then we will add that one, or PCU would be, oh, PCU would be 2592, 2592, then 6 zeros, then divided by, you add that to 324, 234 plus 262,500. So PCU is 441.94 Newton. And then from the equation 1, P aluminum is equal to 800 minus 441.94 is equal to 358.06 Newton. So this is our force for the copper, and then this is for the aluminum. Now going back to his problem, actually he sent this question with a solution, but when I first saw this one, let me check. So if you notice, his force for aluminum is 3.14 kilonewton, and then 4214 for the um I don't know if A is aluminum, then if B is copper. Now if you notice, the given the load is only zero point 0.8 kilonewton, but his answer is 3.414 kilonewton. So that's already a mistake. And then although his solution is correct, maybe this is during, if you notice, 3414, that is almost 3414. What is our force? 358. I think maybe when he rounded off his equation or answer here, because you should not, I would say, you should not round off your number unless that's the final answer. If he did not round it off this number, it's probably correct. The value is correct, but the unit is wrong because this is kilonewton. So again, we have two formulas for strain, depending if it is acted by a force, which is PL over AE, And then if it is acted upon by like just a change in temperature, like internal force, which is due to change in temperature, then you have your alpha change in temperature, and then the initial length. I hope this is clear. Um, so if you have questions, just let me know. Goodbye, mga lagan.